Hi, let's talk a little bit about polarization. What polarization is when all the waves are all vibrating in the same direction. Like they're all vibrating up and down, or they're all vibrating left and right, or all vibrating at some angle. Doesn't matter as long as they're all vibrating in the same direction. And so unpolarized light is sometimes represented like this, where some of the waves are going up and down, some of the waves are going back and forth, some are going at different angles. And so you can see where this kind of picture comes from. The arrows represent that the waves going up and down or left and right. We call that unpolarized light. Well, this is a polarizing filter. A polarizing filter is a filter that's got atoms kind of lined up almost like a picket fence, like you would see on like around a house or something like that. Just these slats going through. So when this light hits it, this will actually block some of the light and let some of the light pass through. And since these are all vertically aligned, we get vertical light passing through this first polarizing filter. Now the question is how much of this light, if this is 100%, how much of that light makes it through? Well, a lot of times people think, well, it's only one of, let's see, one, two, three, four lines. So is it a quarter? And no, it's not. It's actually more than that. What happens is these waves that are at the angle, if we do a little bit of trig, some of that wave's going sideways and some of that wave is going up. This part that's going up still makes it through. So it ends up being that you have about half the light making it through that first polarizing film. So now all the light is vibrating up and down as it passes through that film. Now let's say we got a second polarizer. And this one we turn sideways so that now the slats are horizontal. Where these slats were vertical, these slats are horizontal. And this polarized light that's going up and down hits this polarizer that is oriented horizontally. How much light gets through now? Well, actually none of it will make it. So between these two polarizers, we can essentially block all the light. One single polarizer can only block 50% of the light, but two of them together can block all the light because it'll block all the vertical and all the horizontal if you set them up at right angles to each other. Now, the human eye cannot tell the difference between unpolarized and polarized light. Just our eye doesn't have the capability of doing that. Bumblebees can, and some other things can actually see polarized light and tell the difference between light that's oriented vertically and light that's oriented sideways. We see light that is polarized, but we can't tell that it's polarized. If you ever wore Polaroid sunglasses, they talk about Polaroid sunglasses eliminating the glare. Well, let's say that we've got this the road or a pond or something, and light's coming in. Light can come in vertically, or if I could do sideways, let's say this is sideways. Can't really tell. One's going up and down, the other one's going back and forth. When both these beam of lights hits the ground or the water or whatever, which one do you think will be reflected off to create glare? Well, if you think about skipping a stone on water, you throw the stone like this, it's not going to skip, it's just going to sink in. So this vertically oriented light will just hit the table and get absorbed and nothing happens to it. But the light that's going side to side, that's like throwing the rock sideways. That is going to skip off and become the glare that you see. So your Polaroid sunglasses will want to block sideways light. So to block sideways light, that means the Polaroid filters need to be aligned vertically. So it only lets vertical light through, which is okay. The horizontal light is your glare, so it blocks that, and so that you don't see it, and you can get a much clearer view of the world. Let's take a look at another couple of examples of where polarizing light shows up in your everyday life, and you just simply don't know it exists. One example where we use polarized light is if you ever go to a 3D movie, you get glasses like these, okay? and you put them on, and the way they're designed is that one lens is polarized one way, the other lens is polarized the other way. They're not vertical and horizontal, they're kind of like angles. But this is another polarizing film, and I don't know if you can see it through this, and I don't think you can at all. Let me see if I can put a piece of white paper there. And oh, I don't think you can see it with me just holding it up here. But what happens is one lens is polarized one way, the other lens is polarized the other. So this eye sees what this camera did with that polarizer. This eye sees what this camera filmed with this polarizer, and your brain puts it together and you get 3D vision. Now, I don't like wearing these because they don't fit well over my glasses, so I need something bigger. So I much prefer to use, instead of these. These are much better. They fit all the way around my glasses, okay? And on this one, I don't know if you can actually see where one lens is completely dark, the other one you can see through. And if I change it, it should switch depending on where I turn it. See, that one, the left is dark and you can still see through the right. But here, the right is dark and you can now see through the left. We'll try this again later with some polarizing films that I've got some white light behind and see if that works better. Okay, so let's try those demonstrations to see what they look like. Here's another example of where polarization works. So if I take this polarizing filter and put it over my calculator, you can still see it clearly, but watch if I rotate it. See, the screen kind of disappears. And it comes back. So that screen for the calculator is polarized. Here, they're all lined up the same, but here, the two polarizing filters, the one on the screen and the one in my hand, are now at right angles to each other. And so no light can get through. Another example is my computer screen. Now you see it, now you don't. So again, that light is polarized. So polarized light is every place except our eyes can't really detect it. So we can't tell the difference. Bumblebees can, but not humans. Okay, I got two polarizing films. Right now, they're both aligned the same way. So you can see me right through there. But if I put one this way and one that way, you probably can't tell the difference much from the light because our eyes can't really tell the difference. But watch what happens when I'm putting them together and then turn one at a 90-degree angle. It doesn't matter which one I turn, but it'll go away because it stops all the light passing through. Now if I get them at right angles to each other and take a third polarizing film, if I put it in front, nothing. I put it behind, nothing. If I put it in between, if I can put them in between, here we go. Can you see me now? What happens is the light gets turned as it goes through. It vibrates this way through the first plate. The middle one makes it go this way, and the third one has it go that way. So a very little bit of light goes through and eventually rotates around. So now remember, polarized light only vibrates in one direction. In vertical slats, we'll let vertical light through. Horizontal slats will let horizontal light through, but only those through. So vertical slats will completely stop horizontal light. Horizontal slats will completely stop vertical light. Glare that you see on the road or anything like that from the sky is polarized horizontally. And so you need vertical polarized sunglasses to block it. And we use polarized light for different applications like on calculator screens, computer monitors, just loads of examples that we use it for, but you just simply don't notice because our eyes aren't designed to detect the difference in vertical polarized light versus horizontal polarized light, right? Thank you, and tune in again later for a little bit more physics.